oh, I recognize that value. Okay. So if as just an aside here, if we were to go to the unit circle, there's only like there's actually a finite number of values that these equations can take on, and they all come from the first quadrant here. So like a lot of students, they don't think about this, but it's if you just look at the first quadrant here, your answers are 0, 1/2, √2/2, √3/2, and 1. And then you also get the reciprocals of these. Now, 1/0 is undefined. Um, this is 2. This is 2/√2, which so you have to rationalize it, which becomes, I didn't leave myself enough room here, but it becomes √2 when you rationalize it. This one is 2/√3, which when you rationalize it becomes 2√3/3. And then this one is 1. So there's actually like not that many answers that you should be able to look for, but it really helps if you, as the student, recognize that the reciprocal of this gets you back there, the reciprocal of that gets you back there, and then you also have the ratios to consider. So I don't know if they talked about that in class, but that saves you some time to be able to do that. So the reason that's so important is because the equation that we solved back in the beginning, it's really the same as where is the cosine of theta equal to √3/2. The advanced approach here is you draw a unit circle and you realize that that's the x value there, and you figure out those angles, pi/6 and 11 pi/6.
Um, if you scroll up a bit, could you explain how you got the 0 to 1 and then numbers in between?
Reciprocals, the flips. So that's the
But how did
secant.
you know that you had to write down 0, 1/2, √2/2, and √3/2?
These are the sine and cosine values. So these are the sine and cosine values. These are the cosecant and secant values. And then there's even more for tangent and cotangent. I mean, it's not an infinite list, but there's, because there's some repetition, like with the reciprocal 1 is 1. So there's only 4 new values. And then tangent and cotangent, you end up getting some repeats.
Mm-hmm.
So there's like 5, 4, I don't know, let's say there's like 12 total, to remember, like all the possible values. I mean, you're a little late in the game. Is your test tomorrow?
Yeah.
Okay. I mean, I don't think I would tell you to, but I just like you want to familiarize yourself. Like these aren't like there's only so many values that it can be.
Mm-hmm.
And so with the
Yeah, I
tangent
understand. I
cot
was just confused why you like wrote it out. I thought it meant
okay,
something else.
so like tangent and cotangent, the other ones are you can get √2/2 over √2/2, which is really 1. That's a repeat. Or you can get
Mm-hmm.
1/2 over √3/2, which is 1 over √3, which becomes √3/3. Or you can get the other one, which is √3/2 over 1/2, which is √3. So there's, like I said, there's only like so many of these values that you can get. Like this is new, this is new, that's a repeat. There's only 11 possible answers you can ever get with sine, cosine, secant, cosecant, tangent, cotangent. And I can mark them here to be clear. 0, 1/2, √2/2, √3/2, 1, undefined, 2, √2, 2 √3/3, √3/3, and √3. Those are the only possible answers you can ever get from a sine, cosine, secant, cosecant, tangent, cotangent problem. But more
Yeah.
importantly is you have to be able to backfill to like what they actually come from. Like like it's not good enough to know that, oh, it's √3/3. It's like, no, that came from 1/2 over √3/3, because that's how you know where to find it on the circle. Thoughts on that?
That makes sense.
Okay. So let's look at 11 here. Um, so the thing with 11 you should notice right away is that uh, you you have you've got mixtures here. You got cosecant and cotangent. So do you remember how to move between those?
Yeah.
All right, so there's three Pythagorean identities you need, and it's like, oh, there's one. Um, that's why this test is hard. There's like a built-in, like you got to know a lot of stuff, a lot of stuff. Um, so cosecant squared is really 1 plus cotangent squared theta minus 2 cotangent theta equals 4. There's often the question like, which one should I substitute for? Should I substitute for cotangent or cosecant squared theta? You always substitute for the square. That's generally the idea here. So moving some things around, when you subtract 4 from both sides, you get minus 3 equals 0. Factoring is a pretty common technique here. Do you remember how to factor something like this?
Wouldn't you use the not the theorem that's like minus b plus or minus b squared?
No, this is just a more standard factoring. Two numbers that multiply to the last but add up to the middle.
Um, minus two and minus one. So it'd be
Those
cotangent
th-
minus
those
two and then
those don't multiply to minus 3. They have to multiply to minus 3 but add to minus 2.
oh, minus three and plus one. So it'd be cotangent minus three and then cotangent plus one.
Yes. Okay. Um, so now you set those both equal to 0. And cotangent theta equals 3, cotangent theta equals -1. I didn't do that right, but anyway. So on the unit circle, tangent and cotangent, they're reciprocals. So we're really trying to figure out like where tangent of theta equals -1, because the reciprocal of -1 is still -1. And that occurs on this line right here, which is 3 pi over 4 and 7 pi over 4.
Mm-hmm.
Is that okay? Because the next one's
Yeah.
harder. So cotangent of theta is 3. If you looked at a graph of cotangent, you would recall that it does kind of snake down like that. So it definitely hits 3 somewhere. But it's like where in the unit circle, where it's positive in the first and the third quadrant. So it's actually not a known value. Like if you go back to that list, there's no place where it is, even if you change it to like tangent theta equals 1/3, we don't know where that is either. So the answer here is that theta is the arctan of 1/3, which, or the arccotangent. You could also do it as the arccotangent of 1/3. Um, Either one is fine. But then
Would it
that's only
not
the first.
be arc cotangent of three?
Yeah, 3. Yeah, that's right. Um, so that gets you the one in the first quadrant. To get the one in the third quadrant, you're adding pi to it. So it looks weird, but that's the correct answer.
Okay, that's what we would write down, or would we plug it into the calculator?
Well, if you're allowed to. I mean, I wouldn't allow a calculator on this. I mean, but that's not, no, that's side point. Like, point is you can do it by hand.
Okay.
I mean, it doesn't mean, I mean, like, in the real world, we would never give this as a, well, the angle is cotangent inverse of 3 plus pi. Like, that'd be super, super awful to see that in a report. Any thoughts on that?
That makes sense.
Okay.
And then we did the same thing for tan theta equals -1.
Well, it's you pick one or the other. You can either do the answer in terms of tangent, which is more common. Most calculators don't have a cotangent inverse, and if they did, they're just calling on tangent.
Mm-hmm. Okay.
So, like I'm not seeing a problem. Like 5A and B, did you do any symbolic problems like those
Which
where you have to
ones?
like where you had to draw the triangle, like cosine of the arc sine of like x over 2? Did you have any problems like that where you had to draw a triangle?
Yeah.
Okay. So like we should do one of those. So that you always make the substitution. You let theta equal the innermost thing there. And then when you take the sine or whatever it is of both sides, to undo the arc sine or arc cosine or arc tangent or whatever, you get sine theta equals x over 2. So you always draw a triangle, some sort of right triangle. I usually draw the one in the first quadrant, and then you label the sides x and 2. And then you have to solve for the third side using Pythagorean theorem. A squared plus b squared equals c squared. So in this case, you don't know a, but you know it's x squared equals 2 squared. So a squared equals 4 minus x squared. So this equals the square root of 4 minus x squared. And the reason you need all that is theta. Theta is really this middle thing in here. So you're actually finding the cosine of theta, which is root 4 minus x squared over 2. Now, a lot of times students ask me like, when am I ever going to use this stuff? And I never really have a good answer because I won't. But if you take calculus 2, almost every
Mhm.
calculus 2 student forgets how to do this. And this is an integral part of doing part of that course. So, like if you want to take more math, you just do it. And then, when you get calculus 2, you're like, oh yeah, makes sense.
Yeah.
Okay.
Okay.
So on to the other side of the page there. We really didn't spend enough time last time talking. Let's keep it really simple here. Let's say it's the cosine of 1/4 x equals -1/2. Okay. So where on the unit circle is the x value -1/2? What are the two values there? Do you have a unit circle handy?
Um, one sec, I need to get one.
Okay. Let me drop it in the chat here. Um,
The two places where
this cosine is -1/2. Like
um
like like think of this as really
two
being
pi
cosine.
over three and 4 pi over 3.
Okay, so 2 pi over 3 and 4 pi over 3. But in your problem, it's 1/4 x equals that and 1/4 x equals that. Because your inside function isn't theta, it's something else. So
Hmm.
in this case, you multiply by 4 on both sides, 4 and 4, and you get x equals 8 pi over 3 and x equals 16 pi over 3. Okay. Are these in the interval from 0 to 2 pi?
No.
They are not. So,
So there'd be no real solutions.
right. And so that's one possibility. Okay, so the other type of problem you'll see, let's say it's sine of 5x. That's probably too big. Let me make it 4x. Let's go 2x. Okay, sine of 2x equals negative root 3 over 2. So where on the unit circle is sine 2x equal to negative root 3 over 2? Or where, I'm sorry, where's just sine of theta equal to negative root 3 over 2? So that's the y value being
4 pi over 3 and 5 pi over 3.
that sounds right. So this time you set the 2x equal to that. And you can see here that you're going to multiply by 1/2 times 1/2. And this time the angles get smaller. All right. So this is where you've got to recognize, oh, I might have a problem here because this ends up being 5 pi over 6. I might have a problem here because, well, when these get smaller, that means there's like more angles to consider. Like it's not really, the answer is really, I hate, I haven't done this well, but the answer is really 2x equals 4 pi over 3 plus the period, which is 2 pi, and it's 2x equals 5 pi over 3 plus the period, which is 2 pi. Now, depending on the problem, you actually put a k here.
Why
You
would you
guys,
add the 2 pi again?
because we're going to see that there's more than these two solutions.
Okay.
It sounds like you didn't cover this in class.
We did
And
it a different way. Like, she would have us write it out. Like, it'd be 2 pi over 3 and then comma 5 pi. I mean, 2 pi over 6, comma 5 pi over 6, comma, and then we'd keep going until
problem
we
is
hit 2 pi.
that pattern doesn't work. Like um, this doesn't increment by the same amount. They individually increment by the period. Not like sometimes there's a pattern between them, but not in this problem.
Okay.
So I mean what I'm trying to get at is like and so the way your teacher showed you is correct sometimes, but not always. Um, I guess what I'm wondering is like, should I even proceed by you know, like forget about this K for a moment. You just need to at least extend it a little bit. So when you divide or multiply by 1/2, you're also multiplying the period by 1/2. So it's 2 pi over 3 plus pi. And then it's same thing on the right here. It's 5 pi over 6 plus pi.
Okay.
And then you do have to actually figure this out. Like this ends up being 5 pi over 3. Ends up being 11 pi over 6. And those are still in the interval from 0 to 2 pi.
Mm-hmm.
Any questions on that?
No, that makes sense.
Okay. Um, so there's some other things here that we haven't talked about, but sometimes you'll get like a cosine theta equals like 2. Like the problem will work that out, and this has no solution. Is it clear why that has no solution? It's really based on the graph of this. Can the graph ever hit 2?
No.
Right. And you see the same thing with like secant of theta equaling, you know, 1/2 because the graph of secant of theta is something like this, and there's 1/2, and it never hits. So sometimes there's like the appearance of a solution, and like what you don't want to do is say, oh yeah, it's theta is the cosine inverse of 2, which there is no solution to that.
Okay.
Right. Let's look at 12. So 12 is yet another set of formulas to have to remember. So I showed you the Pythagorean identities earlier. You're also expected to know the uh, double angle and half angle. Well, probably double angle more than anything. Formulas are usually the ones for just sine and cosine. Let me go to this here. Like without this, you might as well just not, I mean, you just couldn't do it. So um, you always substitute in for this one here. But the question is like, well, which one should I use? And it really depends on what's on the other side of the equation. So in this one, I would use this one right here, the middle one, because it's just cosine. So you've got cosine x equals 2 cosine squared x minus 1, like that. And then your
Mhm.
general strategy is to get everything on one side of the equation. So you've got cosine squared x, 2 cosine squared x minus cosine x minus 1 equals 0. And then you have to factor those. Could you attempt to factor that for us, please?
So needs to multiply to -1, but also add to -1.
This is so that doesn't work because there's a 2 in front. It's really considered a grouping problem, but I would use the guess and check approach because you've only got one factor of cosine. Um, so it's either going to be 1 here where my cursor is, or a -1, or -1 and 1, or 1 and -1, and just sort of guess and check until you find it.
Two cosine x plus 1 times cosine x minus 1.
Yeah, that'll do it. So then from here, you set each of those equal to 0. And you get cosine x equals -1/2, cosine x equals 1. You got to go to your unit circle for those. Um, Cosine x equals 1 is going to be on the nice part of the unit circle. And then -1/2 is going to be a couple of different places, right? It's going to be there and there. Which again is one of those where it doesn't go up by like the same amount each time. They're not really related.
Okay. And then I would write the answer as
Well, all the possible ones. So just whatever you got here, whatever you got.
so the answer would be minus 1/2 and 1.
Where for what angle is the cosine of that angle minus 1/2? And for what angle is the cosine of that angle equal to 1?
Oh, okay.
Like where on the unit circle is that true?
Um, 2 pi, 2 pi over 3, and 4 pi over 3.
So I'm sure I commented somewhere that, it's really super critical to know your unit circle. And that this is, you can see why. It's like really, like that's just one little piece of this question. Any questions on that? Take that as a no. So 17 here. Reason I'm bringing up this problem is it's not it's not the case that you can use Pythagorean identity because they're not squared. So the question is like, how do you like combine these? Sometimes you have to go back to sine and cosine. And this is where you actually will be doing this in the next chapter. You'll be doing like these things called proofs. But in this chapter, what this allows you to do is kind of rewrite it in such a way that you can maybe make a little more sense of it. So if you multiply both sides by sine x, you can see that they cancel there. You get 1 minus cosine x equals sine x. Is that okay so far?
Yeah.
Okay, there's a couple ways to solve this from here. One is to look at the graph. Graph of sine is that it does this. Cosine, it's flipped and it's moved up one. And what you're going to see here is that, um, I guess we should do that here. So flipping cosine, if you flip it, it comes up, down like that. And if we move it up one, you can see that they actually do hit, but they only hit there and there. So it actually does have a solution. Now, there's another way to do this as well. I don't know if you would know or want to do the graph. The way to do it without doing what we just did is to then you can square both sides and you get 1 minus 2 cosine x plus cosine squared x equals sine squared x. And then you can change sine squared x into 1 minus cosine squared x. And so then you get some better stuff. You end up getting the ones cancel. You move that over, so you get 2 cosine squared x minus 2 cosine x equals 0. You can factor out a 2 cosine x from both, and you get cosine x minus 1 equals 0. So 2 cosine x equals 0, cosine x equals 1. And the problem is not all of these are solutions. So you end up getting extraneous solutions because this is at minus pi, which we know it actually does work. But it's not in the interval. This one's at 0. So I would
Okay.
recommend using the graph. Like that's a really complicated way of doing the problem. Like I would like if you get it down to something kind of reasonable. You also will keep in mind that a lot of your solutions are on the unit circle, on like the nice parts of the unit circle. Those are always good ones to check, just to get that partial credit.
Okay.
All right. I debate where to go from here. Um, yeah, I have no idea. So, Nature's nuts. These are yeah, it's all too much stuff here. Right. So these are triangle problems again. Like if you let theta equal arctangent of 4/3, then the tangent of theta is 4/3, which means that that's 5. So then the sine theta is 4/5, and you can sort of manipulate these problems doing this. Um, does this look at all familiar to you?
Yeah.
Okay. So, um, I just even set what to do from here. Um, so in another triangle, it becomes sine theta is x over 1. So you have uh x over 1. This becomes the square root of 1 minus x squared. And so the arctangent of that, I actually don't know what your instructor wants here. Did you get any notes on this?
No, wouldn't the answer just be 4/5?
It it could be. I feel like there could be a little bit more to it. Truthfully, I'm a little tired, so I don't know if I can give this the full effort. But yeah, maybe ask, real quick before your
Okay.
test. Um, so all right. What we do have to stop here, unfortunately.